Good morning, friends. I am Vijay Choudhary. Currently working in IPS Academy. I have been here for last 10 years. Today we are going to discuss a very important subject, that is analysis and design of algorithm. This subject is taught in BTech second year normally, maybe they are in third sem or maybe they are in fourth sem. But as far as placement is concerned, as far as other competitive exams are concerned, this subject is very important. So I hope you will enjoy the learning of this subject. We are going to study analysis and design of algorithm, abbreviated as ADA. That stands for analysis and design of algorithm. Okay, so friends, as the name is suggesting, we are discussing about the algorithm, its design, and at last the analysis of the algorithm we have designed, right? So as the name is suggesting, it is analysis and design of algorithm. First of all, for doing that, we need to understand what is algorithm. So we first start with the algorithm. What is algorithm? So algorithm is nothing but the sequence of steps to be followed to complete a particular task, right? Or to complete a particular work you have given, right? So it is sequence of steps to be followed to complete a task. Right? So it is well defined sequence of steps. As I have told, we cannot say it as set of steps, right? Because in case of set, the sequence is not important. That is why I emphasized on this sequence of steps to be followed, right? That means the sequence is very important here, right? We need to focus on the sequence also. So we need to mention all the steps to be followed to accomplish a particular task, right? Similar thing, if we study the programming languages, then similar thing comes into the picture, and that is program. So many students get confused in that. What is the difference between an algorithm and a program, or these two are same things, right? So I would say these two are not same things. There are some differences between the two, right? Now let us discuss the differences. So first I would write about the algorithm, and then I would write about the program. So as far as algorithm is concerned, right, we design an algorithm, right? So algorithm is designed. So we design an algorithm. As far as a program is concerned, right, we implement a program. Second thing, if we talk about algorithm, then for writing or designing an algorithm, domain knowledge is required. So whoever is writing an algorithm must have knowledge of the domain, and he can write the algorithm, right? As far as program is concerned, we need programming knowledge. So who writes a program? A programmer writes a program. And a domain expert design an algorithm, right? Okay. So third thing, if we talk about, then here an algorithm is language independent. Right? There is no bar for the language. Any language which can be understood by the person in front of us can be used for writing an algorithm or designing an algorithm. As far as program is concerned, it is specific to a particular language, right? Like if we are using C language, then it would be a C program. If we are writing a Java program, then we need to use Java language specifically. So it is language dependent. one program cannot be used universally or for all the languages, right? So it is language dependent. So if we come to algorithm, right, then it doesn't depend on the OS being used and the hardware we are using, right? But as far as program is concerned, it highly depends on the OS being used, right? Because we have seen if we are using Linux operating system, then some other language would be used. Same other version of the same language would be used. Like if we talk about C, then different C would be there for the Linux and different C would be there for the Windows operating system. So there will be difference. So here it highly depends on the OS being used as well as, so I would write depend on the OS and hardware, right? So these are some differences, right? Here if we talk about algorithm and program, right? I hope this would be clear to you, right? So in short, if we talk about the difference between an algorithm and a program, then an algorithm is more generalized form for doing a particular task, while a program is a specific solution for a problem, right? It depends on the language being used. It doesn't depend on the language being used. It depends on the language being used. It doesn't depend on the hardware or software. It depends on the hardware or software being used, right? So these are the differences between algorithm and program, okay, right? So I think it is clear to you. Now we move forward. We would be focusing upon the algorithm mainly. It is just the closed term, that is why we discussed about the program also. We would be focusing on the algorithm, that is more generalized form of the solution of any task given to us, right? So that is algorithm, right? So we would be focusing upon that. Now if we talk about the algorithm, then a good algorithm must possess some characteristics. And which are these characteristics we are going to discuss. Now the characteristics of an algorithm. Number one, input. Every algorithm we are designing or we are creating must have 0 or more inputs. Why I am saying it as 0? 0 means it may be possible that we are not supplying any explicit input, right? But there may be some inbuilt or inclusive input for that. So 0 or more inputs required for an algorithm, it must be there. So first thing is input. Number two, output. There must be single output corresponding to an algorithm. It can be combination of multiple part of the outputs, multiple outputs, small outputs, but overall it would be a single output that would be generated at one time, right? As far as any algorithm is concerned. So output, there must be a single output. Output must be there. We cannot say 0 output. So any algorithm must generate an output. That output may be in the form of display only. For example, if we are using any language and we are just displaying the name of the students studying in IPS Academy, right? So we are just displaying the list, right? So there is no explicit kind of output. We are just displaying the list over there on the board. So in that case also the output is there, right? So it doesn't mean explicit output. We are catching that output in some variable. It is not necessary. There can be some display sort of thing also, but there must be some output generated by the algorithm we are designing. Number 3 is definiteness. our algorithm must be definite. That means it must be unambiguous and must show some specific things, right? That means there should not be any kind of ambiguity. Like many times, if we talk about the language, many times we say something else and some person may understand something else. But here there is no scope of such kind of thing. So your algorithm must be definite. That means it must be unambiguous. It should lead to a single meaning only, so that compiler understand it and execute it properly, right? So there must be definiteness in the algorithm. And then finiteness. Many times it happens, we always wanted to terminate the thing that we have started, but accidentally it happens that we design some code or we write some steps which is not actually terminating something somewhere, right? So we must have the block of code in such a way that it terminates somewhere, right? Many times you must have heard about the infinite loop as far as any programming language is concerned, right? So many times we just write a small block of code, and what we see, it is there in the infinite loop if we run it, right? So it should not happen here in case of algorithm also, right? If we are writing some steps for the algorithms, they must run finitely. That means there must be some finite time where the execution of the algorithm ends, right? So there should not be infiniteness in the algorithm. That means it should not repeat the block of code indefinitely, right? So you must have some criteria, you must have some stop point where it stops and terminates, right? And then the most important thing is effectiveness. It is also sometimes called conciseness. That means every step of your algorithm should be meaningful or should lead to a particular task, right? Definitely, if there is a big task, we divide it into some smaller tasks, and the block of codes or the steps we write for the algorithm serve some purpose, right? So your algorithm must serve some purpose. It must be effective, or it should focus upon a single concern that it is designed for, right? So that is called effectiveness. It must serve some purpose. It should not be meaningless, or it should not be unnecessary step that we have written in the algorithm, right? So these are some characteristics we must understand or we must know before understanding the algorithm. Now, till now, we have discussed about what does it mean by algorithm, how it differs from that of the program, and then we come to the characteristics that a good algorithm must possess, right? And now we come to the main part, that is analysis part of the algorithm. That means we have designed the algorithm, but how efficient, how useful that algorithm is, now we will be discussing in the analysis part. Now here it comes, analysis of now the analysis of the algorithm depends on actually the category of the algorithm. If we talk about the categories of algorithm, then broadly we can classify it into three categories. First one is sequential algorithm. Second one is iterative algorithm. And the third one is recursive algorithm. Now one by one we discuss which are these categories actually. First, if we talk about sequential algorithm, then in case of sequential algorithm, each and every step of the algorithm is executed once only. That means there would be no repetition of these steps involved in this, in such kind of algorithm, and these algorithms are said to be the most efficient one, right? As we know, each and every step would be executed once only, so there would be no complexity involved over here, right? So most efficient type of algorithm where statements executed once only. Number two, iterative algorithm, as the name is suggesting, repetition sort of thing is there, right? So here we would be having the block of codes which will be repeated for definitely finite number of times, right? So that is our necessity, that it must execute finite number of times. So but though that would be more than once, there would be block of code which would be repeated again and again for some finite number of times. So this comes under iterative algorithm. These are less efficient than that of the sequential algorithms. Now the third category comes recursive algorithm. Here recursion is involved. You must have heard about the recursion. Recursion is nothing but repetition of the method itself by itself. That is called recursion. So here the algorithm would be calling itself again and again for a finite number of times, right? So here it would be the strategy where we'll be solving the problem by calling the algorithm itself again and again by itself. So this is recursive algorithm, and that is again less efficient than that of the iterative algorithm. So these are the three categories mainly we are going to discuss for analyzing an algorithm also. So different types of algorithm would be having different type of strategy for analyzing, right? So first of all, if we talk about sequential algorithm, there is no problem at all, right? Single iteration would be there, right? Most efficient one, so nothing to worry about and no need to calculate the time requirement also. It would be having the constant time requirement always. Now if we talk about the analysis, again we come to the point. Now if we talk about the analysis of algorithm, two types of analysis can be there: priori analysis and posteriori analysis. Priori analysis is where we analyze the algorithm, or we analyze the things while designing it, right? So it happens there in case of algorithms. So in case of algorithm, what we do, we perform priori analysis. That means at the time of design of the algorithm, we perform this analysis. So this is called priori analysis. Definitely before the deployment we are doing that. That is why it is called priori analysis. And posteriori analysis is something that we perform after the development of the things, or after the development of the algorithm or program we have designed. Here this is used by the programs generally. So if we talk about algorithm, then we go for priori analysis. As far as programs are concerned, we go for the posteriori analysis, right? So here we do the analysis. That means we analyze the algorithm using priori analysis, and as far as program is concerned, we perform testing. That means we are doing priori analysis on the program. So these are the two categories of analysis. So mainly we are going to focus on the priori analysis of algorithm. Now if we talk about the analysis, then we must have some measuring criteria for analyzing that algorithm, right? For example, for measuring the length, we are having centimeter, millimeter, kilometer and all, right? Similarly here, in case of analyzing algorithm, we must have some parameter. So here the parameter that we use is called complexity. Generally we perform the analysis and we analyze the efficiency of anything, right? Like the program efficiency, what is the program efficiency, what is the algorithm efficiency, or if we talk about any machine, then we talk about the efficiency of that particular machine. But here we do this in reverse manner, we are talking about the complexity that is inversely proportional to the efficiency of an algorithm, right? So our measurement criteria would be complexity, not the efficiency, right? So we can say efficiency is inversely proportional to the complexity. I think now some clearance is there regarding the complexity, what is complexity actually, right? So definitely if it is inversely proportional to the efficiency, that means what our motto would be, what will be focusing upon would be the minimization of the complexity. Generally what we do the maximization of the efficiency, but here we'll be doing minimization functions. That means we are trying to minimize the things here, because our measurement should be minimized for efficiency of the algorithm, right? So complexity we are going to use, this would be the measure for analysis of algorithm. Now what complexity is actually, right? So the complexity, generally the students have misconception that a complexity is the time required or space required for executing or for running a particular algorithm, but it is not actually. The complexity is not that quantity of the time required or that quantity of the space required for an algorithm, but it is the change in the growth rate of the time or space requirement in the algorithm, right? So I would be focusing upon that first. So what is complexity? It is the change in growth rate of time or space, right? So it should be clear now, the concept must be clear that it is not the growth rate, it is the change in the growth rate, right? So and it is not the time required, it is not the space required, but it is the change in the space or change in the time required with change in the input, right? So this is the complexity, algorithm complexity if we talk about, right? Second, if we talk about type of complexity, then there are two categories. Space complexity and time complexity. Right. So if we talk about space complexity, then space complexity is nothing but the space required at runtime for execution of an algorithm with the change in its growth rate, right? So it is not only the space required at runtime for executing an algorithm, but it is the change in the growth rate of the space with change in the input for the algorithm, right? So it is the growth rate, change in the growth rate, of space with input. Similarly, if we talk about time complexity, then it is change in the time requirement with change in the input, right? So it is change in time with change in input, right? So these are the two categories, space complexity and time complexity. Now the point is, why do we need space complexity? Time complexity we are going to discuss in detail, right? So first we discuss in short that what is the requirement of space complexity. Then nowadays we are having enough space. Generally we don't bother that much about the space complexity, but if we are using using multi-user environment, if we are working with multi-user environment, in that case it becomes mandatory to mention the time space requirement of the algorithm, right? So in that case it comes into the picture, यहाँ पर importance रहता है. Second thing, if we need to check whether we are having enough space for executing a particular software or not, in that case we must have the idea about the space we are having, right? So we must know the space requirement of a particular software that are going to be used here, right? So we can say whether we are capable of doing that or not, right? So these are the 2 points where this space complexity becomes important. But nowadays we don't bother that much about it. So we would be focusing more upon the time complexity of an algorithm, right? That means directly related to the efficiency. Okay, right? Okay. So time complexity we are going to discuss in detail now. Definitely it is change in time with change in input. So that much time would be there. The change, if higher change would be there, then we would say the complexity is higher. If lower change is there, we would be say the complexity is lower. So what our motto is to lowering down this complexity. That means the change should be minimum, and we say that algorithm is efficient if that change is okay. As we have some predefined constructs, as in all the languages and all, we have predefined functions and all, we are also having here some predefined categories of complexity, and by looking at into that category, we can say the algorithm which belongs to that particular category would be more complex than the algorithm belongs to some another category. So based on that, so we are going to discuss some popular categories of the complexity which are there. So if we talk about the category of complexity, then it would be first constant time complexity. Constant time complexity, generally represented by order of 1. Number 2, logarithmic complexity. Logarithmic time complexity, represented by log n. Then linear time complexity, represented by order of n. Then polynomial time complexity, represented by n to the power k. In general form, I written over here k. K can be any constant, right? And at last it comes the exponential time. And it is represented by some constant k to the power variable n. Actually here the n represents the input size. Here n represents input size, right? And here what we are interested in is what would be the change in time with the change in that input size, right? So that is why n we have taken as the variable, and according to the change in the n, we would be observing the change in the time or change in the space. So here we are talking about the change in the time, right? So first, the most efficient type of complexity comes, that is constant time complexity. As the name is suggesting, there would be no change in the time requirement with change in the input size. It doesn't matter whether the size of input is 10 or it is 10,000, right? The requirement, the time requirement would be the constant, and it is considered to be the most efficient algorithm. If we understand this thing graphically, then we can understand it like this. If this axis covers the input n, and this covers the time t. Then as far as constant time algorithms are concerned, the graph would look like this. We increase the number of input or size of the input, there would be no change in the time requirement. So it would be like this, always straight line parallel to the horizontal axis. Next, logarithmic complexity. There would be slight change, there would be some change with change in the input size. If we increase the input size, the time requirement would also be increased, but not with the order of the input, right? So the magnitude would be little bit lesser than that of the magnitude of the input, right? So that is logarithmic. I would represent this as order of 1, order of log n. Right. Next, linear time complexity comes. As the name is suggesting, linear change would be there. That means with the same proportion, the time requirement would change with the same proportion of the change in the input size, right? So like if the input is changing with the same proportion, the time is also changing. If you increment the input, increase the input, time requirement would also be increased with the same proportion. So it is linear time complexity. Then polynomial time complexity. The curve would look like a parabola. That means a slight change would have large impact on the time change, right? So if we increment, if we increase the number of input, then the time would increase more than that of the input increase, right? So input, if we increase input by 20, then it may be 40, 60 or 100 also. So it would be order of n to the power k. It could be n square, n cube, n to the power 4 or n to the power k, whatever, right? So that is polynomial time complexity. And the last one is exponential time complexity. That means as the name is suggesting, a slight change may have a drastic change in the time requirement. So a small change may lead to a large change in the time requirement. So it would be some constant k to the power m. So this is exponential time complexity. I hope these categories are clear to you, right? So definitely here I have written it in a sequence. If we move from up to down, then the complexity would be increased, right? And if we move from bottom to top, it would be decreased. So I have shown it in a graph also. I hope it is clear to you, categories of the complexity. So definitely if we say an algorithm belongs to this polynomial category and an algorithm belongs to this logarithmic category, we can definitely say that this algorithm would be better than that of this. So no need to go further in detail, right? So we can easily understand this. Now we are analyzing the algorithm, different categories of algorithms, right? Then we need some mathematical notation to represent the complexity, right? What we have studied so far, we have studied what does it mean by algorithm, then what is the analysis of algorithm, then what are the categories of algorithm we are going to analyze, okay? And then now we are then we discussed about the measure which we use for analyzing an algorithm, and that is what the complexity, that is inversely proportional to the efficiency, okay? And then now we need some mathematical measure to represent the complexity that we are interested in, right? So for representing the complexity of an algorithm, we need some mathematical model or mathematical construct, and that mathematical construct is asymptotic notation. These are the mathematical notations which we are going to use for expressing the complexity of an algorithm. Right. So in short, we would be discussing the asymptotic notations also. So what the asymptotic notations are? First of all, we need to understand why these are called asymptotic. Asymptotic means what? Very large. Asymptotic means very large. That means whatever the calculations we are going to do here would be on relatively larger values. That means the input size would be relatively larger, right? So that is why we are going to use asymptotic. That means we don't bother if your algorithm performs badly on small inputs. We are interested in it must perform well if the input size is large. That is why we are going for asymptotic notations, not simple notations. So for very large notations we are going to give here. Now, if we talk about asymptotic notations, then we are going to use three kind of notations. Number one, big O notation. Number two, omega notation. Number three, theta notation. One by one, we understand the things. Now, first we talk about the big O notation. Then big O notation is used for worst case analysis of an algorithm. You must be knowing about the worst case. First, we can discuss it. Right? So any algorithm can have three cases: worst case, best case, and average case. Right? That means for different inputs, there may be the worst performance for some set of we can say for some set of input, the algorithm may perform worst. So that would be the worst case of that algorithm. Right? Maybe some set of inputs for that your algorithm give best results, right? So that would be the base case of that algorithm, right? Then average case. So for some set of inputs, it may perform on an average behavior. It exhibits on an average behavior. So that would be the average case. Yeah. It would be more clear if we take one example of, say, searching, right? If we are having 100 objects and we need to search some object, right? So maybe then there can be, so depends on the arrangement of the input, there may be different cases for finding out that particular object, right? May be possible that object is situated there at the first place of your list or your container, right? So for the first try we get it, right? So that would be the best case of your algorithm, and we are starting with the first one only. So we are moving, like we compare with the first, then second, third, fourth, and we keep on comparing until we find the object we are searching for, right? So if we are lucky enough to find it at the first place itself, then that is the base case of that algorithm. Right? May be possible that object is situated somewhere in between in that container or in that list, right? So that would be the average case of that algorithm, right? May be possible that we have applied an strategy that we are starting from the first object and the object that we are searching for is situated at the last place. So in that case we would be unlucky, and that case would be the worst case, because we would be comparing all the n-1 objects, right, for finding out that single objects among the n objects available, right? So these would be the different cases. So every algorithm can have all these cases: worst, best, and average cases. So as far as this big O notation is concerned, we use it for expressing the worst case of the algorithm. And listen it carefully, that the worst case is the most important case as far as computer science is concerned, because we can guarantee it that would be finding it in that particular point time, right? Like if we talk about these three cases, जैसे मैंने searching का example लिया था, in that searching example, right, if I want to give the guarantee that we would get that particular object in that span of time, in that case I need to give the worst case time, because maybe if we are lucky we get it at the first place itself, maybe it is situated somewhere in between to the list, or if we are not lucky enough then we would get it at last place. So if I want to give the guarantee that I would get it in that time, then I would say you the time of the last place, that is the worst case. So that is why we always focus upon the worst case, because it gives you guarantee that it is not going to be stretched more than that. So that is the highest stretch of the time, right? So Big O notation is used for worst case complexity representation, right? It is represented by Big O, and if we express it mathematically, then we would be writing like the magnitude of f of n would be smaller than or equal to that of some constant c times g of n, where n is very large than some value n0. Yeah. So before understanding this inequality, we must understand what are these f of n and g of n are, right? And c is some constant, right? So f of n is nothing but the growth rate of the algorithm we are working with, right? And g of n is a standard curve or a standard polynomial that we have taken, which is very much closer to that of the actual curve f of n, right? So f of n is what? It is the growth rate of the algorithm we are dealing with, right? Actual growth rate of the algorithm we are dealing with, and g of n is some standard growth rate which we have taken for calculation of the growth rate of the actual algorithm, right? So g of n is what we assume, right? And it must have some criteria, like it must be closer to the actual curve, right? And we take the worst one if worst and better is available, right? We go for the worst one, and also n should be very much large. So these should be the three criteria while selecting this g of n. I hope now it is clear. F of n is representing the actual growth rate of the algorithm. G of n is some standard growth rate that we have taken for comparing, right? C is some constant. So what Big O notation says, the growth rate of the actual curve should be smaller than or at most equal to that of the g of n that we have taken. So if we understand it in graphical form, then we can say it would be like this. If this is the curve for g of n, then this would be the area where f of n would lie. So somewhere here below that curve. So at most it may touch it, right? But it would be below most of the time. So that is what Big O notation represents. Next one is omega notation. It represents the best case complexity. And for finding out the best case, best means what? We are searching for an element and we find it at the first place itself, right? So that is, in that case, in that case, we must know the whole algorithm in advance. So that is the precondition that for calculation of the omega notation or the best case complexity, we must know the algorithm in advance. So complete algorithm must be known. Here, if it is not known completely, then it is okay. But in case of best case, we must know it in well in advance. Right? So in case of best case, right, the inequality would be just a reverse of it. That is, f of n, magnitude of f of n would be greater than or equal to some constant c times magnitude of g of n. So if we draw a graph corresponding to that, it would be like this. If it represent g of n, then the f of n would lie here somewhere above this curve, and it, at most it will be equal to this curve g of n. Now the last but not least, it gives you the exact time complexity theta. If we talk about theta notation, if we are representing the complexity in theta notation, that means we are giving exact complexity. That means more accurate than that of the omega as well as big O notation. Right. So as far as theta notation is concerned, the magnitude of f of n would be greater than some constant c1 times g of n, and would be smaller than some constant c2 times the magnitude of g of n for all n very large than some n0. Right. We go for theta notation for exact, as I have said, right. And second thing, if there is slight difference in the worst and best case behavior of an algorithm, then we go for the theta notation. So this is how these notations are. I hope this is clear to you all. Now we are going to use these notations to represent the complexity. As I have told, most of the time we are much interested in big O notation. That is why most of the time we see the complexity is expressed in the form of big O notation. So big O of n, big O of log n, big O of n square and all, right. It is because of the importance of that worst case. That theta notation also in the graph. So there could be some graph, say c1 of gn, and this would be the graph of c2 of gn. Then f of n would lie here in between in case of theta notation. Last topic of our lecture, that is how to calculate the time complexity of an algorithm, right. So as we have seen, there are three categories of algorithms: sequential algorithm, iterative algorithm, and the last one is recursive algorithm. So as far as sequential algorithm is concerned, we need to just count the executable statements and just write down that this is the complexity of that, and that doesn't change with time. That is always constant time. So no need to calculate that complexity. It is always constant time, right. Second, iterative comes, and then recursive comes. As far as recursive algorithms are concerned, we are going to use recurrence relations. And based on that, by solving that recurrence relation, we are going to calculate the time complexity. We are not going in detail with that recursive algorithm. We are going in detail with the iterative algorithm. Now the topic is how to find out the time complexity of iterative algorithm. So there are some steps which we need to follow to calculate the time complexity of iterative algorithms. Number one, find out all executable statements of the algorithm. First, we need to find out, there may be number of statements like the comment section which are not being executed, right? We don't count those because they don't affect the complexity of the algorithm. So first we need to find out which are the statements which are executable actually, right? So first step is find out the executable statements, right? Number two, second step, find out the number of times the executable statements are executed, or we can say find the frequency count of each and every executable statement. Find out the frequency count of each and every executable statement. Number three, add all executable statements to find out the frequency count of whole algorithm. And the last step is use asymptotic notations to represent the complexity in single term polynomial. So these are the 4 steps for calculation of the complexity of an iterative algorithm, right? First, find the executable statements. Second, find the frequency count of the executable statements. Then add all the frequency counts of the algorithm to executable statements to find out the frequency count of the whole algorithm, and then go for the asymptotic notations for expressing the complexity. Now, we take an example and we understand how to follow these steps. Some variable, say x equals to 0, some variable I equals to 1, and now we are having some input from the user, and then we are having a loop, while I is less than or equal to n. What we have to do? We have to increment the x by 1 and also increment the I by 1. So this is small block of code or a small algorithm that we have written. Now we have to find out the complexity of this code, right? So, so what is the first step? The first step is find out the executable statements. Right? Now, what are the statements which are actually executing? So x equal to 0 we are assigning. So this would be one executable statement. So we mark it. So this is one executable statement. Then we are assigning 1 to I. This is also another executable statement. Then scanf %d, and we may or may not consider this as executable statement, and as the input is being taken from the user, right? So we may not consider it, so we are not considering it. It doesn't actually matter, right, whether to consider it or not. Now next, while I is less than or equal to n, we are comparing I with the n here, so this would also be one executable statement. Then x, we are incrementing x by 1, this would also be an executable statement. I is also being incremented by 1, this is also another executable statement, right? So we have identified in this algorithm there are 5 executable statements. Then, so this is step number 1. Now we come to step number 2, that is find out the frequency count or the number of times these executable statements are being executed. So as far as the statement number 1, x equal to 0 is concerned, it is being executed once through the lifetime of this algorithm or program, right? So the frequency count of this is 1 only. What about I equal to 1? This is also the same, once throughout the lifetime of the algorithm. So this is also 1, right? Now we are not considering this as the executable. Now this statement comes while every time we are comparing I with n. कब तक compare करना है? Till we are having I greater than n, right? As far as I is smaller than n, this would be executed, right? As soon as I becomes larger than n, then it would not be executed, right? So this is also an executable statement. Now number of times it is being executed, right? So if we talk about this I, then the value of I is 1. So if value of I is 1, then it is okay, it would be inside this. So suppose n is 5, right? So if n is 5, then if the value of I is 1, then it is okay, the condition is 2, and then we are inside the while loop, right? So in that case it would be true. If then it becomes 2, 1 I plus 1, 1 plus 1, that is 2. Now again 2, for 2 it is also true, for 3 it is also true, for 4 it is also true, for 5 it is also true, but for 6 it is not true, right? So till 5 this condition will be true and will be entering into the loop, but as soon as the I becomes 6 in this example, then this condition would be false and will not going to enter into the loop, right? But this statement would be executed for that that false condition also, but once, right? So if the value of n is 5, it would be executed 1 more than 5, that is 6 times. So if the value of this is n, then it would be executed by n plus 1. I hope it is clear, right? So as far as this condition is concerned, it would be executed more than n times, n plus 1 times, I would say, right? So it is executed n plus 1 time. But how many times we get entered into the loop? It is exactly n times, because for n plus 1 time, it would not permit you to enter into the loop, right? So as far as these two statements are concerned, these would be executed n times only. I hope it is clear. There is a difference between the frequency count of this statement and these statements which are inside the loop, right? So this would be executed exactly n times, this would also be executed n times. So this is the second step we have discussed, right? Now the third step, that is find out the frequency count of the whole algorithm by adding the frequency count of all the executable statements, and we represent it as function of n. As I have told already, that n would be our variable, because n is the input, and based on the change on that input, we are monitoring the change in the time, and we are measuring the complexity, right? So f of n, that is the frequency count of the whole algorithm, being represented by f of n, because it is function of n, that is why I am writing it like f of n, would be the summation of all the frequency counts. So it would be the frequency count of statement number 1, frequency count of statement number 2, and then n plus 1, then n, and then n. So total, the frequency count of whole algorithm would be 3 plus 3n. So this would be the frequency count of the whole algorithm. Now step number 4 that I had written, according to that, use the asymptotic notation to represent this frequency count into a single term polynomial, and we can go for any asymptotic notation, but generally we use big O notation, so that is why we are going to use here also the big O notation. So the complexity would be big O of, if here we can see constant time complexity is also available and linear time complexity is also available, we would go for the worst one, that is the linear time complexity. So the complexity would be order of n as far as this block of code is concerned. It would be big O of 3 plus 3n, that is big O of n, that is order of n. That means linear time complexity would be there. If you increase the number of input, the time would also be increased with the same proportion. Clear? I hope it is clear to you. So this is how we calculate the time complexity of iterative algorithm.